Section 8.1, Chemical Bonds, Lewis Symbols, and the Octet Rule. There are three types of chemical bonds. You have ionic bonds. Ionic bonds are essentially electrostatic forces, so like static electricity that's holding the ions together. You've got a positive and a negative, and they're attracted to each other, so they stick together just like socks in a dryer. You have covalent bonds, and covalent bonds result from a sharing of electrons between atoms. So both of these atoms have electrons in their shells, and the shells are overlapping, and the electrons are free to move back and forth between the shells of the different atoms. The metallic bond refers to metal nuclei floating in a sea of electrons. So the metal atoms are bonded to each other slightly, and then they're holding lightly to the electrons. So the electrons are free to migrate around, in fact, even travel on the outside of the entire metal, and that's what's traveling when you have something like electricity in a wire. Lewis symbols. The electrons that are involved in bonding are called valence electrons. Just like a wedding veil is on the outside of the bride's face, valence electrons are the outer shell of electrons, the outermost shell. So you find the valence electrons are normally in an incomplete shell. So if you were to have a group 8 electron where there would be exactly 8 s and p electrons, s subshell and p subshell electrons, then you would have a full shell. Then normally they would not bond at all. But with an incomplete shell, you tend to have bonding, and the reason is because we'll see in a minute with the octet rule that you need a stability of a full shell. The full shell has a stability that all atoms are seeking as they react with each other. So the valence electrons are only the s's and the p's. If you remember, an s subshell only has one orbital, so that means there's 2 electrons in an s subshell. A p subshell has 3 orbitals. That means there's 6 total in the p subshell. And so if you have an s and p together, you have 8, and that is what you're going to see in the Lewis structures. The Lewis dot structures are going to show the valence electrons around the symbol of an element. So if you were to have something like neon, okay, neon is in group 8, it'll have 1, 2, 3, 4, 5, 6, 7, 8. But chlorine is in group 7, so it's going to have 1 unpaired electrons. It has 3 sets of paired, 1, 2, 3 sets of paired electrons, and 1 unpaired electron. Carbon is in group 4, so it's going to have 4 sets of unpaired electrons. If you were to have chlorine like we looked at a second ago, and it's got 7 valence electrons, it's going to have 3 pairs of non-bonding. So this is non-bonding, this is non-bonding, this is non-bonding, and then you have a single one here. It's an unpaired electron, and an unpaired electron is just begging to form a bond. So for instance, if you had a hydrogen up here with 1 in its outer shell, and it will easily join with that chlorine and make a hydrogen-chlorine bond, and a bond is a sharing of 2 electrons. The octet rule. Representative elements such as anything in S subshell and P subshell columns are going to seek to be the most stable that they can be, and they tend to react over and over again until each atom in every compound has 8 electrons in its valence shell. This is called the octet rule because 8 is an octet. So if you were to have neon, for instance, neon is in group 8. Neon is so stable that there are no neon compounds. Neon is not diatomic. It's one atom floating around, totally happy to be who he is. He doesn't seek to be a compound. There's no advantage for him to combine with anything else. So it's a stable atom. Well, if you have something like chlorine, chlorine has three paired electrons and one unpaired electron, and it will react with everything. It's one of the most reactive elements in the whole periodic table, and it is so because it has a hole here in its stability factor. It has an octet is not filled. It's an incomplete shell. And because it's an incomplete shell, it will continue to react until it has a configuration equal to neon. As soon as it's like neon, it's stable and it stops reacting. So an octet rule is a kind of a driving force in bonding because every single atom is tending to become as stable as it can be. And the most stable you can get is an octet that's filled. Now the exception to this would be group 1. Group 1 has hydrogen, has 1 electron, helium has 2 electrons, and that's all. There's nothing else. So you can't have an octet in the first shell. The first shell is stable at 2. So helium is in the noble gas column. It's in group 8, and it's very, very stable, but it doesn't need 8. Every other element under helium that's also noble gases all have 8 in their valence shell, and so everything will tend towards that full shell. So hydrogen is wanting 1 to join with, so that, or either steal 1 or share 1 in order that it has a configuration equal to helium. Chlorine is going to steal 1 or share 1 until it has a configuration equal to neon. So the octet is trying to get something to the closest, the configuration equal to the closest noble gas.